Hello everyone. The title of the topic that I'm going to talk about is the development of closed form solutions for modeling the material failure process in beams as hinges by the embedded discontinuity model. This is Ángel, Uriel, Martínez-Miranda, and my co-worker is Gelacio, Juárez-Luna. We are from Universidad Autónoma Metropolitana from Mexico. The outline of this presentation is as follows. I will give a brief introduction to the subject, then I will talk about kinematics, then constitutive models, then the variational formulation, closed form solutions, then about validation examples, and finally conclusions. New design methodologies in structural engineering have highlighted the need to develop new techniques to study the nonlinear response of structural systems under severe static-dynamic loads. The nonlinear behavior begins when the acting loads produce internal stresses that reach the threshold values of strain of the materials. Once the strain of materials is exceeded, the process of material failure begins, preceded by a strain localization phenomenon, characterized by the formation of strain concentration zones in which damage and other inelastic effects are concentrated. These zones gradually turn into physical discontinuities in the continuum. In case of beams, the study of the failure process has led to the development of advanced mathematical models such as Armero and Ehrlich, Nanacorn, Scott and Fenves, Pitar, Juarez, among others. These models had been approximated by numerical methods. No attempt had been made to study the problem as it was originally done for any physical problem under study, that is, developing closed form solutions. That is why in this research we develop closed form solutions. The developed closed-form solutions are based on the strong embedded discontinuity model, which was originally introduced by Simo and Oliver. To understand this model, the kinematics of the embedded discontinuity model for beams is first presented. Consider a thin beam with a prismatic form of a three-dimensional solid reduced to a one-dimensional reference length, which has the boundary conditions as shown in the figure. This beam is loaded until it undergoes to a discontinuity across a surface. This discontinuity is modeled as a hinge. There is a rotation jump, as seen in the figure, where a stress-strain nonlinear constitutive relation describes the material behavior. The material surrounding the discontinuity is described by linear elastic standard constitutive models. The kinematics of thin beams with strong discontinuities is represented by a discontinuous rotation with its corresponding rotation jump at S, as shown in the figures. Then the discontinuous rotation is given by this expression, and the curvature is the derivative of the discontinuous rotation, so that the Dirac delta function is naturally obtained. Therefore, the curvature is given by this expression. As in thin beam, a thick beam is now considered with a prismatic form of a three-dimensional solid reduced to a one-dimensional reference length, which has the boundary conditions as shown in the figure. This beam is loaded until it undergoes to a discontinuity across a surface S. In the thick beam model, the effect due to shear strain is taken into account. Therefore, the discontinuity is developed as a hinge and/or a dislocation, which are represented by a rotational jump and a transverse displacement jump, respectively, as in the figure, where a stress-strain nonlinear constitutive relation describes the material behavior. Again, the material surrounding the discontinuity is described by linear elastic standard constitutive models. In the kinematics of thick beam with strong discontinuities, in addition to the discontinuous rotation and curvature defined for thin beams, it is considered the discontinuous transverse displacement with its corresponding transverse displacement jump at S as shown in the figures. Then the discontinuous transverse displacement is given by this expression, and the shear strain is the derivative of the discontinuous transverse displacement minus the discontinuous rotation, so that it is given by this equation. The constitutive model for beams are defined based on the moment-free energy density, which is given from moment curvature relationship, and on the shear free density energy, which is given from shear force shear strain relationship. Then the moment and shear force are defined as these equations. When the beam element is undamaged, these relationships are assumed to be linear elastic. Consequently, these relationships are defined for these equations. When the beam element is damaged, these relationships are defined based on the standard constitutive models, introducing a damage variable t, which can be a scalar, vector, or tensor, which quantifies the damage occurred in the continuum. The damage variable is defined from a softering rule, which can be linear, exponential, among others. The proposed variational formulation is based on the Lagrangian mechanics, which consider a Lagrangian function that for quasi-static loads is defined as the opposite of the potential energy. The potential energy is defined as the opposite of the work done by the stress or force with respect to an associated strain or displacement. All the potential energies for thin beams consider the potential energy due to elastic behavior, the potential energy due to external loads and body forces, and the potential energy due to nonlinear behavior. Note that only bending energy is considered for thin beams. Then the Lagrangian function for thin beams is defined for this expression. The time-volume integral of the Lagrangian function is defined as this equation, which represents the variational formulation of a problem. Then the Lagrangian function for thin beams is remembered here, which is defined for this equation. Therefore, the time-volume integral of the Lagrangian function is defined as this functional, which represents the proposed variational formulation for thin beams. Now, the first two terms of the right-hand side of the functional are defined as integrals through the domain. However, the last term is defined as a surface integral at the discontinuity. For this reason, it is necessary to modify the functional to use the conventional analysis of calculus operations. In order to achieve this, a special unbounded value is considered, which is the gradient of the rotation discontinuity. This gradient is considered as a special unbounded value because a strong discontinuity model assumes that there is continuity between the subdomains of the beam. When an unbounded special value is considered, the Dirac delta function is used to operate mathematically. In this case, the main restriction of the Dirac delta function is considered, which is defined as this expression. Then, if the main restriction of the Dirac delta function is used, the surface integral is now defined as an integral through the domain. Therefore, the variational formulation leads to the following functional, in which the conventional analysis of calculus operation can be used. Just as it was developed for thin beams, the variational formulation for thick beams is now developed. All the potential energies for thick beams consider the potential energy for linear elastic behavior, the potential energy due to external loads and body forces, and the potential energy due to nonlinear behavior. Note that in addition to considering the bending energy, shear energy is now considered in this case. Then the Lagrangian function for thick beams is defined for this expression, and just as the variational formulation of thin beams was developed, the proposed variational formulation for thick beams is given by this functional. Whenever a variational formulation is proposed, in which conventional methods of calculus operations can be used, we proceed to obtain the differential equations that define the problem. The differential equations are obtained when the functional given in the variational formulation has a stationary value. The functional of the proposed variational formulation of thin beams has a stationary value by Euler-Poisson system of equations, which is given by these expressions, where L is the Lagrangian function and Y is the independent variable of the Lagrangian function. Well, substituting the Lagrangian function of the functional for thin beams into the Euler-Poisson system of equations, the system of differential equations of thin beams with discontinuities is obtained, which is given by these equations. The first differential equation is defined for linear elastic behavior, and the second differential equation is defined for the nonlinear behavior. From the system of differential equations of thin beams with discontinuities, the closed form solutions of the transverse displacement, the discontinuous rotations, the bounded bending moment, and the bounded shear force are obtained. These closed form solutions are expressed in terms of the constants of integration which depend on the boundary conditions. The rotation jump is expressed by a softening rule which can be linear, exponential, among others. Here, some closed-form solutions are presented for different boundary conditions in thin beams. For example, a cantilever beam with distributed load, a cantilever beam with concentrated load, a simple supported beam with distributed load, and a fixed beam at one end with simple supported at the other one with distributed load, a simple supported beam with concentrated load, and a fixed beam with concentrated load. Just as it was a payload for thin beams, the functional of the proposed variational formulation of thick beams has a stationary value by Euler-Poisson system of equations. Substituting the Lagrangian function of the functional for thick beams into the Euler-Poisson system of equations, the system of differential equation of thick beams with discontinuities is obtained, which is given by these equations. The first two differential equations are defined for linear elastic behavior, and the last two differential equations are defined for the nonlinear behavior. From the system of differential equations of thick beams with discontinuities, the closed form solutions of the discontinuous transverse displacement, the discontinuous rotation, the bounded bending moment, and the bounded shear force are obtained. These closed form solutions are expressed in terms of the constants of integration which depend on the boundary conditions. The rotation and transverse displacement jumps are expressed by a softening rule which can be linear, exponential, among others. Here, some closed form solutions are presented for different boundary conditions in thick beams. For example, a cantilever beam with distributed load, a cantilever beam with concentrated load, a simple supported beam with distributed load, a simple supported beam with concentrated load, and finally a fixed beam with concentrated load. We present two examples. The first example consists of a simple supporting beam with a concentrated load at the center of the span with a thickness of 1 mm and geometry as shown in the figure. The mechanical properties of the beam are these. The history of the transverse displacement at the center of the span obtained from the closed form solutions is compared with the beam finite element with discontinuities developed by Juárez and Ayala and with the two-dimensional 6-node plane stress triangular finite elements developed by Wells and Slush. As you can see, the curves agree. The following figures show the closed form solutions for the entire beam element for both cases thin and thick beams. Here we present the transverse displacement for thin beam, thick beam, rotation for thin and thick beam, curvature for thin and thick beam, and shear strain for thick beam. The second example consists of a fixed beam on which a load P is imposed at the center of the span, as shown in the figure. The beam has a length of 2 meters, width of 0.1 meters, and height of 0.2 meters. The mechanical properties of the beam are these. The history of the transverse displacement at the center of the span obtained from the closed form solutions is compared with the beam finite element with discontinuities developed by Juárez and Ayala. Again, as you can see, the curves agree. The following figures show the closed form solutions for the entire beam element for both cases, thin and thick beams. Here we present the transverse displacement for thin beam, for thick beam, the rotation for thick and thin beam, the curvature for thin and thick beam, and shear strain for thick beam. As a conclusion, a variational formulation of the material failure as hinges in beams was developed. Closed form solutions for benchmark problems of thick and thin beams were developed. The developed closed-form solutions adequately model the history of loads and displacement. These closed-form solutions provide the behavior of the beam element from the initial loads to the collapse of the element. In the development of the closed-form solutions, it was shown that there is a direct relationship between the strong discontinuity model and the discrete discontinuity model. In the application examples, the load displacement curves computed with the developed closed-form solutions are in agreement with the numerical solutions reported in the literature. And if you want to know in detail the research carried out, please refer to this paper. Thanks for your attention. If you have any questions, please contact us by email. Thank you.